Okay, welcome to the final part of this unit. We are going to study here magnetism and electricity, but specifically the connection between the two. Okay, there's a connection. That's the first thing you need to know. It's a special connection. It's between magnetic fields and not just charges, but between magnetic fields and moving charges. So underline moving. Here's one of the two connections we'll see. A charge that moves, whether through empty space or filled space, whenever the charge moves, it produces its own magnetic field. It's weird, but it happens. Whenever the charge stops moving, the magnetic field disappears. And the faster the charge goes, the stronger the magnetic field. Those field lines make loops or circles. Because all magnetic field lines cannot terminate because they don't have anywhere to end. There's no monopole, there's no north pole isolated from a south pole. So they can't end anywhere because there's no pole at which to end. So they just keep going in a circle. Now, this video is really good. It demonstrates it. It is, however, wrong. There's one small thing which is wrong. So let me go all the way to the beginning. So that right there is a charge. At the very start, it's not moving. So you don't see any magnetic field lines. You don't see any circles. But when it starts moving to the right, watch what happens. It starts moving, and now there are these field lines being produced around the charge. And check it out, the field lines make circles, they make closed loops, like we expect. And they make kind of like they make concentric circles around the charge. And then when it slows down, there we go, when it slows down, those field lines disappear. So when it stops moving, we have no more field lines. Look at all those videos. Now, a couple of things that are wrong about this. This is a great animation. There's a couple of things that are wrong. The faster the particle is going, the faster the charge is going, because this is charged now. It has to be charged to produce a field, a magnetic field. The faster the charge moves, the stronger the magnetic field. Okay? The stronger the field, the denser the field lines, the more closely spaced they are. So let's watch this video. Is it correct? Are the field lines more closely spaced when it speeds up? And are they farther spaced apart when it's not going very fast? Let's watch and see. So it's not going very fast, and those are pretty close field lines. And then it speeds up, and it looks to me like the field lines are getting farther apart. So this is backwards. The field lines should be closer spaced. So imagine like lots and lots of field lines really packed together the faster it goes. And then here when it slows down, those field lines sort of disappear and fade away. And we have wider spaced field lines. Okay, back to our notes. We will consider not just we will consider the field produced by moving charges, but we won't consider very often any field produced by just one charge. In most cases, we are going to have tons of charges flowing one after the other. We'll have a whole current in a wire. Okay? So here's how this works. There's my wire. Current is flowing up through the wire. We always imagine that the current is positive. So imagine that there are positive charges going up through the wire, right? And so every single positive charge has those fields around it, those circles, those magnetic field lines. And what that causes is sort of like these columns, these cylinders. I mean, there's not just magnetic field lines right here. There are magnetic field lines a little bit above and a little bit above. So there's a whole column of field lines if we drew them all in. But here we're only showing the concentric circles at two specific points along the wire. So how do we figure out which way the field lines point. We know they make circles, right? But how do we know which direction those field lines point in? For example, all we've learned so far is that the field lines make these loops, which are kind of perpendicular to the wire, right? The loops kind of are perpendicular to this wire, or the plane of each loop, each set of loops. This first set of loops lies in a plane which is perpendicular to the wire. But how do we know if the lines go clockwise? I guess this is kind of counterclockwise, or the other way, clockwise. Which way do those lines point? Here's the way you figure it out. You use the right-hand rule. That's how we find the direction of the B field. So the right-hand rule says, take your thumb, point it in the direction of the current. The wire is up, going straight up, and the current is going from bottom to top. So your thumb points up, where the current goes. Then you hold your fingers straight out, whoops, not like shown here, but straight out, like you're about to give someone 5, or shake a hand. And then once your fingers are out, you curl your fingers into your palm, and that's what this picture shows. They've been curled in toward the palm. The direction in which your fingers curl, in this case, our fingers were out here, they were straight out, and then they curled in. That direction is the same as the direction of the B field. We'll practice this. This is a much better picture showing it. Look at this. On the left side, we only have 2 sets of concentric circles. Concentric circles mean that there's a bunch of circles and they're all centered on the same point. And we only have 1 set here and a second set here. But in fact, there are field lines at every point along the wire because there's charges moving at every point along the wire. And so this is not the picture on the left is not very accurate. Instead, a better representation is like this. Those field lines make kind of a column of lines, right? There's like a whole column extending up and down. Now here's the thing about the column. The loops, so here's 1 set of loops, and those loops are not evenly spaced. Successive loops become farther apart. Here's what I mean. The first loop here and the second loop here, those 2 are closer than the second is to the third. And the third loop is even, so the distance between the first 2, this distance, is smaller than the distance between the second and the third. And the distance from the second to the third is smaller than the distance from the third to the fourth. So each successive loop is farther and farther away than the previous one was. They become more widely spaced. And that's because the magnetic field is denser closer to the wire. Excuse me, let me say that again. It's because the magnetic field strength is greater closer to the wire. So the bigger the magnetic field strength, which we call flux density, the greater the magnetic field strength, the more dense the field lines, which means they're more closely spaced, close to that wire. They're really, really close here, right? We're almost at the wire, so the spacing is really small. They're dense, and as we go farther and farther away from the wire, here's the wire. Now here my mouse is really far away. Here, those field lines are less dense because the strength is not as big. Strength is weaker. Okay, so imagine we take this long wire, here it is, and you bend it into a circle. What does it look like? It looks like this. The field lines look kind of like a donut. Ignore this. And we've got a few more pictures that show that. Here's one, and we're evaluating just two loops rather than a bunch of loops. Okay, so we have to be careful because there's the loop of the current, and then there are the other loops, the concentric loops of the magnetic field. So here are just two current. Here's the current loop, the blue, and then here are two magnetic field loops. Looks like a tambourine. Okay, how do we use our right-hand rule to figure out the direction of the field? Here's the way you do it. Imagine our current loop is like so, and the current is going in and then around this way and then back out. At this point, the current is moving to the right, kind of along a tangent to the circle. So you point your thumb to the right like the picture shows. your fingers are straight out, and you curl them in to find the direction of the B field. So your fingers would go up, and then they would come over the wire, which means they would do sort of what's shown here. At this point, right? At this point, the thumb points in. Let's see. I guess we're actually like right here. The thumb points like this in the direction of the current. Your thumb is parallel to the current, so the current is kind of moving at a tangent at this point right here. So your fingers, they start out straight, and then you curl them. Whoops. They start out straight, and then you curl them up toward your palm, and you find that they're curling over around the wire. And that's why, if we look at the right, we see that those field lines kind of curl over around the wire, And on the outside, they go down. On the inside of the wire, they go up, because your fingers would be going up on the inside, and then they would curl around, going down on the outside of the wire. Okay, if we looked head on, imagine, so here's the wire, right? Imagine we have current going around like this. Here's what our field would look like. We would have, on the inside, the field would be coming up, or let's say, it's coming out of the page. On the inside, the field lines are coming out of the page. And the dot there means that the field lines are coming out of the page, like shooting out of the screen. If you were looking in 3D, it's like, whoa, duck your head, because the field lines are coming at you. They're coming out of the page, out of the screen, and then they loop around the current, so they don't quite hit you. They turn and they loop around before they hit your face, and they kind of come back into the page over here on the outside of the current loop. Okay. We will deal with this more in class. We'll practice this. We'll get our get our thumbs pointing in the right direction. You'll practice curling your fingers when you solve your problems, your practice problems. In real-world settings, when you bend a wire into one single loop like that, you don't make a very strong field. So this is not a very good way to produce a powerful magnetic field. Instead, we don't want a weak field. We want a strong field. So instead, we don't just bend it into a one circle. We bend it into lots of circles. We get a really long wire and just keep looping it around. Loop, 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 loop. So many loops. This produces what we call a coil, or a fancier word, so that we sound smart at parties, we call it a solenoid. Right? The magnetic field of a solenoid is identical, in fact, to the magnetic field of a bar magnet. Check this out. That's so cool. So imagine that our, in this case, current is going, it's starting down at this end, and the positive charges are moving through, and they exit right here at the top. So you can practice using your right hand rule, right? Try this point right here. You point your thumb in the direction of the current, which is sort of like into the page, kind of like this. And then your fingers would curl out and around like that, in the direction where my mouse is going. And that is no different from the kind of configuration we see for a bar magnet's field lines. They're almost identical. So just like a bar magnet has north and south, this sort of has north and south. South is where the current starts, the positive current. North is where the positive current leaves the solenoid. South is where it enters, down here. And here we have that exact same thing shown, but with the right-hand rule drawn in, right? At this point, where you see those blue lines, the current is moving up, and so you put your thumb up, your fingers curl in and then out, and that's why you get in and then out. So on the inside, your fingers are moving in, so the magnetic field lines point in to the left. To the left, they go in, and then on the outside of the solenoid, your fingers would curl back out, just like this shows, if you had like really long stretchy fingers. Okay, and that's it for this video. You might be wondering what this is. This shows that right here, the current is moving into your face, like out of the page. It's coming out toward you, and then the current loops around and is heading back in right here. Don't worry about those. The important thing from this picture is those field lines showing where your fingers would be curling. So the magnetic field lines is what's important.